Hi there, and welcome to our first lesson on physics. Before we get into anything too specific, we want to generally talk about what physics is so that we can help focus our eventual lessons after this point. And so I ask you very broadly, what is physics? In many ways, we often think of it as the science of motion, the science of energy, the science of force. It is all of those things, but in many ways, it's really about how the physical world behaves, the rules that govern how matter and energy interact with one another and what happens because of that interaction. I guess that's kind of a good sort of summary. And so let's write some of this stuff down. Here we are, and we're starting with our introduction to physics. And we're trying to give a definition of physics. We're not necessarily giving the best definition, but one that means something to us. Essentially, in its most basic things is how things work. What things? How physical objects behave and interact, if you will. And of course, these objects I'm talking about could be subatomic particles or vast galaxies or anything in between. What physics is often not is biology. Biology is, of course, the science of living things, while physics has some part to say in that. Biology is its own field, but essentially everything else is in science is kind of physics. Whether we're talking about chemistry or astronomy, these fields of sciences are really just subfields of physics themselves. I would consider biology certainly separate and distinct from physics, so there is a lot of overlap when it comes to biophysics as well. And so the sort of main things that we look at when we look at physics is matter, energy, and we often discuss forces, and eventually what those things kind of interact, how they interact with each other. And so that's a really kind of just an obscure sort of way of defining what we're going to do. Let's get a bit more specific in what physics is by looking at some of the fields of physics, the very general fields of physics. And if you like, you can pause the video at this point and maybe write down a list of the types of physics that you know about. And so we'll call this fields or types of physics. And the first one we're going to talk about is the one that will matter the most at the beginning of first year physics. And that is what is often referred to as mechanics. And so mechanics is really that sort of traditional physics that one thinks of when they think about motion and the things that cause that motion. So something like, a basketball being thrown or a rocket ship being launched into orbit or beyond. These are physics being used to propel something or to understand how things move and why they move and what they will actually do. And this is basically the play between forces and kinematics. And so kinematics is that physics of motion, while forces is the physics of what causes the motion. And technically we call forces dynamics, And kinematics is its own thing. In fact, maybe instead of writing kinematics up there, if it's okay with everyone, I'll move kinematics here. So we'll talk about forces and we'll talk about motion. And so a little bit more scientifically, we'll name kinematics, that study of motion, while forces is essentially the study of what causes the motion. When we think about just kinematics, we're just thinking about motion without thinking about what is causing it. There's other very broad topics in physics as well. The other one that is most popular, I think, is the idea of magnetism and electricity. This is also a very big topic in first year physics. Usually it's one that you find in the second semester of first year physics. And so you'll probably wait for that until your next semester. And along with magnetism and electricity, often we talk about waves and specifically light or optics. Again, something that you'll encounter in your second physics class in university. And so really mechanics is what we will focus on first. Of course, there are a few other fields of physics as well that you don't really get into in first year, but we'll mention briefly here. Definitely we want to talk about quantum physics. And really the physics of the very small is a field in and of itself that's super important. And this would include nuclear physics, particle physics, though in many ways they are handled very differently than quantum physics. You can kind of group them all together as the physics of the very, very small. And then there's the other big pillar of modern physics. So classical physics is basically your mechanics, your magnetism, electricity, optics, etc. And then modern physics is built on two large ideas. The first being quantum physics and the second being relativity. Interesting contrast between the two. Both of these arose at about the same time. They started gaining traction in the late 1800s and really came into fruition in the early 1900s, but their histories could not be more different. While, nuclear, particle, quantum, all of those fields had hundreds of contributions from great physicists from all over the world, relativity, which I'm talking about now, is really just the result of the work of a single person, whom I think you'll all know well, of course, and that is Albert Einstein. And so whether we're talking about special relativity, which is fairly easy to understand and can be learned in first year, or the much, much more complicated general relativity, these ideas are, again, like quantum physics, taking physics to a very specific place that we won't go to usually in first year physics, whether it's very fast or near very strong gravitational fields. It's not something we have space for in our first year class. And so there you have it there. That's sort of our pillars of physics as we know it. There's certainly other fields we could talk about as well. But I want to talk a little bit about the idea of forces, because this is so fundamentally important to the idea of physics. Without forces, you would essentially be looking at a static universe, a universe that didn't change in a sense. It didn't have acceleration. It didn't have things essentially changing from one state to another and interacting with one another. And so forces is fundamental to our idea of physics as it is. And so I'll just make a little note about that. And specifically that now currently we know of four fundamental forces of nature. And these fundamental forces of nature dictate how much of the universe works. The first one, I think we can all guess, fundamentally the one that comes to mind when you think of force, is gravitation. So the gravitational force is clearly for you and me a super, super important force in our everyday lives, from us staying on this planet here to the Earth orbiting the sun, and the way the galaxies work, and the overall structure of the universe itself is dependent on the gravitational force. Now, we're going to look at the gravitational force at the first semester of first year physics on a much more terrestrial level. We're going to take that as our main force on the planet Earth that is going to be a big player in both kinematics and eventually dynamics. In your second semester, certainly electricity and magnetism, or the fundamental force of electromagnetism, turns out they're actually two forms of the same thing, plays the much bigger role. And then the next two you really don't learn too much about in your first couple of years of physics. That's the strong nuclear force and the weak nuclear force. And these are obviously very fundamental forces, but they work on such a small scale that we do not experience them in our everyday lives. They're the forces that work within atoms and within particles themselves. And so we won't deal with any of that stuff. Gravitation will be a big focus for the first semester, and electromagnetism is a big focus for the second. Now, I know some of you are thinking, well, I know a bunch of other forces too. I know the frictional force, or pushing force. As we'll see, those forces are forms of some sort of fundamental force. So those are our big ones. So that gives us a good starting point for talking about what physics is, but let's talk a little bit about the science itself. The science of physics has been around for a long time. You could argue when it started. Some might say Galileo. Some might say Isaac Newton in the mid-1600s really established what physics was. But since then, since at least the 1600s, physics has undergone huge amounts of changes. Now, if you're talking about a science that is essentially studying nature, and you know, your definition of nature might be plants and animals, but my understanding of nature is the natural world itself, and the physical part of that natural world is what physicists are trying to understand. The question is, why has it taken us hundreds of years at least to get to this point? Why was the fundamental physics nature of the universe not apparent right away? Or why didn't we figure everything out in the first 5 years of physics being a thing? Why has physics progressed as it has? And the reason it has is because of experimentation and measurement. Experimentation and measurement is what drives physics forward. Now, clearly there's other fundamental portions to it as well. There's a huge amount of theoretical work that is necessary. Obviously, Albert Einstein wasn't an experimentalist. He was a theoretician that came up with fantastical laws. Isaac Newton, you might definitely say, is both an experimenter and a theoretician. But if you just have physicists working on a computer or on a whiteboard trying to understand the nature of the universe, well, they're not physicists, they're mathematicians then. That's what mathematicians are. They're looking at the way that natural numbers work with one another, but they don't have to actually describe anything physical. Physicists need to be able to describe the physical world, and to be able to do that, to check that their work has meaning, we have to compare it to what's happening in the real world. And so we enter into this very, very productive cycle of observation, like some kind of experiment where you observe something that can't be explained by current theory. And so new theory must be drawn up, equations must be developed and derived, and sometimes guessed at. Hypotheses are made, and those hypotheses have to explain the observations that have already made, but they must also predict other things as well. They have to predict other physics phenomenon as well. And then the experimentalists take that information and they test it. They test all of the theory as much as they can, and that sometimes verifies the theory, and sometimes it finds flaws in it or specific examples where it doesn't work, where it leads to even more theory, and so on and so on and so on. And this has happened for hundreds and hundreds of years. The reason Albert Einstein was able to do his work on relativity is because some stuff didn't make sense. Some things didn't make sense. And so he came up with a theory to allow those things to make sense. But since then, his theories on relativity have been tested hundreds and hundreds of ways, in different ways, and those theories have stood the test of experiment since. Will they? Will we eventually come up with something where it doesn't explain a phenomenon? Sure. It's very, very possible. And then we'll have a new theory that needs to be developed to explain that. And so this has happened over time. And the reason why experimentation has gotten better and better is not just driven by theory, but driven by technology, driven by our ability to make better and better measurements. As we've been able to make finer and finer measurements, we've learned more about the physical world, requiring more physics to explain. And so let me emphasize the importance of experimentation and measurement. And so, as I've said, you need experimentation and you need improving measurements to advance physics. And really all sciences. This is not exclusive to physics. So we require this to advance physics and all sciences. And so, as I mentioned, our ability to measure finer and finer details, to be more accurate in our measurements, has been a major factor in our progress. We are able to see things that we weren't able to see before, whether it's smaller things or finer details. And so we'll capture that as a major factor in the progress of science has been the discovery of better, more precise methods of measurement. All right, that's good. Okay, so what do we measure? What is the stuff that we're measuring in physics? And so yourself, I'm sure you can think of many things. We measure the strength of force, the speed, the acceleration, all of these things. But when you get right down to it, most of what we measure, especially in first year physics and certainly in the first semester, is coming down to 3 basic units of measure. There's 3 quantities that we want to measure that we then use to measure other quantities. So basically what I'm asking is, what are our basic measurements that we make in physics? And all the other stuff that we measure will be made up of these basic quantities. So what do you think? Maybe pause the video if you want to give it a thought here. Let's go over fundamental quantities that can't be broken down any further. Maybe you're thinking about velocity, for example. But velocity is made up of distance and time. It's measured in meters per second. It's not a fundamental quantity that we consider a basic measurement in physics, but both of the quantities that make it up are both distance and time, or as we'll call it, length and time. Very different from one another, cannot be broken down farther. And we'll just mention one more. Just one more quantity is going to help us to talk about all of the quantities that we need in this course, and that one is mass. There are other fundamental measurements as well, but that's going to help us with all of the kinematics and dynamics that we do in this course. And so when we're measuring these values, we need to have a common language. If we're talking about length, we're talking about time, we're talking about mass, we cannot come up with our own units of measure, and those are different from someone else doing a different physics experiment. And so it's important for us to come up with a common language in physics that we can discuss fundamental quantities like length, time, and mass, and be able to share the experimentation and measurements that we are making. And so we are going to use a system of units, and this is the system that scientists use all over the world. There are other units as well that are used depending on the exact field, but for our purposes, we will use the International System of Units. Also known as SI. So SI units, I think it's from the French System International of Units, and the ones that we are concerned with so far are the ones that concern mass, length, and time. And you can probably tell me what they are. Certainly the fundamental SI unit for time, we all know, is seconds. And so we're going to have to define what a second is, but that's going to be our basic unit of measure, given by the lowercase s. Length, unsurprisingly to us as Canadians at least, is meters. And we'll use lowercase m for that. For mass, sometimes people think that naturally it should be grams, but in fact kilograms is our current definition. And so we will use that kg as our fundamental quantity of mass. And so what we need to know now, though, is if this is our unit of measure, how are we going to make sure that 1 kilogram in our laboratory equals 1 kilogram in another laboratory, equals 1 kilogram across the world or on the International Space Station, or eventually when we get further away. How do we define what those quantities are? So now that we've defined the 3 basic measurements that we're going to deal with, length, time, and mass, as well as the units of those, meters, seconds, and kilograms, what we want to talk about is basically how we measure those things. How are those values reproducible from one place to another? And so let's start by talking about time a little bit. And we want to understand what we mean by time with regard to, are we talking about when something is happening, or are we talking about a time interval between 2 events? And so those are 2 different aspects of time that one can consider. The first one, the time interval, that is what we want to discuss in this course. We're always going to be talking about how long it takes between 2 events, as opposed to, exactly what time some event occurs. That's not important. It's what happens between 2 events. So that's the one that we care about in kinematics eventually, but sometimes we consider an instant in time. All right, so that brings us to the definition of 1 second. What is 1 second? Well, there's historically been numerous ways of defining what a second is. The last time I checked, this is how we define a second. Allow me to write this down before. All right, that number says 9,192,631,770. All right, I'm going to say all this stuff. It's unlikely you need to know all this stuff, but please appreciate the precision that I'm going to demonstrate here. Periods of the radiation corresponding to the transition between hyperfine levels of the ground state of cesium-133 atom. All right. Now, you don't really need to know that, of course. But what you're basically hoping you understand is that this is a very, very precise value, that we have, what are we looking at here? At least 9 significant figures giving us a very, very precise value for a second. They take something naturally occurring, a cesium-133 atom, and it has these transitions between hyperfine levels. You don't have to know what that means, but basically understanding that we're able to measure a second to a very, very high degree of precision. All right, so moving on to length. When we're talking about length, there's usually, again, 2 aspects to that quantity that we should appreciate. The first is usually, traditionally, a distance or a displacement. We'll define the difference between those 2 words a little bit later. But this is the change in position or the distance between any 2 points. In many ways, it is very much like the time interval, where we're not concerned about where something is. We want to know what the length difference between two positions are, as opposed to our second thing, which is position. And so we will most often care about that one. Okay, and so then we want to ask ourselves, now that we understand what length is, how long is a meter? Like, exactly how long is a meter? You're like, well, I got a meter stick here. That's how long a meter is. But where did that measurement come from? And if I wanted to be very, very precise, to do very accurate measurements in science, how do I get that value? Well, it turns out that it is also well defined by something natural. This is the length traveled by light in a vacuum during the time interval which I will give. So light is a constant. It has a constant speed in a vacuum. And over the course of a very, very small fraction of a second, 1 over 299,792,458 of a second, light will travel exactly 1 meter. That is the definition of a meter. Notice that this does rely on us knowing how long a second is, of course, but we defined that previously. So it's good. We have ourselves a very, very high precision. Again, 9 significant digits that give us how long the length is. Now I wrote T there. That is the time it takes for light to go that distance. Great, okay. So the last one is mass, and I'm sure we're all thinking in our heads now, what would be a really good way to measure mass? I suppose you could get some very, very stable molecule or element, I should say, and get a very specific number of atoms of that object. It's nothing so complex as that. This one is pretty old-fashioned. Though they are changing it, last I checked, mass, or the definition of a single kilogram, is a single platinum iridium cylinder located in some secret location on the outskirts of Paris. Let's say located outside of Paris. And now I hope you agree with me. That's pretty bizarre that the other two have such an exact natural value that is very much reproducible regardless of where you are. The speed of light can be measured. The cesium-133 atom, you can measure these things with the proper equipment. Yet this definition of a mass is actually just, there's this like hockey puck of iridium, platinum iridium sitting in Paris, and all other masses are in comparison to that mass. And I just think that's hilarious, because that's pretty much, I'm sure, what was happening in the measurements of masses and weights in medieval times. You would figure that a village would have like some set of weights, and they would use that to measure things out when they're, you know, for trade and all of that kind of thing. But it's laughable that this is still the method. But I had heard recently that they are changing it to a more sustainable, reproducible method with a higher degree of accuracy. All right. So that gives us some language and some definition of our basic quantities. Okay, great. So now we're starting to get a little bit more familiar with the language of physics itself, so that we can communicate with other physicists. And there are other shortcuts and bits of language that we use in physics that we need to learn. And one of those is scientific notation. And many of you are familiar with scientific notation. So for example, what I can do with a number that is exceedingly large is to give it in scientific notation to basically save space, to make it easier to understand, etc. So let's imagine that we have a large number like this. That is 3,652,100,000 meters. And as you can see, it's a very large number, but it ends with a bunch of zeros. Those zeros are not significant. They don't give us any additional information. And so what we can do is we can simplify this as 3.6521. You don't have to put these extra zeros because they don't mean anything once you slap on the times 10 to the how many ever units that we've moved over. So for example, if we wanted to go from here, this is where we think the decimal lies, and we want to go 1, 2, 3, 4, 5, 6, 7, 8, 9. We can write that as 3.6521 times 10 to the 9 meters, like so. So don't leave any zeros at the end of your decimal. They don't mean anything. They do not provide any additional information or accuracy, but do include all significant numbers that are basically all non-zero numbers. And essentially try to make this number that appears in front of the decimal between 1 and 9. That is good scientific notation. Above 1, less than 9. And so let me make a quick note of that. This is how I want you to start presenting your answers. Now, if it's a number that is close to a single digit number, whether it's in the tens or the hundreds, you don't need to use scientific notation. So if I calculate a number 555, I would just leave it as 555. If it was above that in the thousands or 10,000s, then I would use scientific notation to make my answer more plain. So the number in front of the decimal, when you're using scientific notation, should be between 1 and 9. All right, so that's super easy when we have a very large number. Is it as equally easy if we have a small number? Yeah, it's pretty much the same thing. Let's say that we were doing a calculation for time, and we found out that our time on our calculator gives us 0.000000913 seconds. And so that's what it says, and we're like, oh, you know, I don't think that is a good way of presenting the answer. How can I use scientific notation to make it shorter and plainer? Well, these zeros here are now extraneous, the ones in front when we have a small number. And so our time is actually 9.13 times 10 to the number of places that we have to move over. And so that's 3, 6, 7. So it's 9.13 times 10 to the negative 7 seconds. And that's great. That gives us the information that we need in a very easy to understand. Now there is another way to give that information. You can use a prefix. You can use a prefix instead of scientific notation if you like. And so one other way to write this that is not scientific notation is 913 nanoseconds. There we go. Did I write that right? A little less. Nanoseconds. 913 nanoseconds is equivalent to 9.13 times 10 to the negative 7. How did I get that? Where did that come from? Well, let's look a little bit deeper at the use of prefixes in physics. Now, I'm not asking you to use prefixes. If you like, you can, but you don't have to. But you absolutely need to be able to read prefixes. Oftentimes in questions, you're given values of micrometers and nanoseconds and decimeters, I don't know, all kinds of different things. And so at the very least, you have to be able to read these. And so let me give you the common prefixes that we use in physics. And we'll make a little chart here of the factor. So this is the value that goes after the times 10 to the 3, times 10 to the negative 6, etc. And here is the prefix that goes in front of it, and the symbol we use to represent that prefix. And we'll start with big numbers like 10 to the 3, 10 to the 6, 10 to the 9, and 10 to the 12. And so this would be like a number you could have 3.2 times 10 to the 9, 3.2 times 10 to the 6. Could I replace that times 10 to the 6 with a single letter that symbolizes that value? Absolutely, because times 10 to the 3 is the same as a kilo. 10 to the 6, that's just a mega. 10 to the 9 is a giga. And finally, 10 to the 12 is a tera. And we do hear about numbers that big oftentimes when we're talking about computers, megabytes, gigabytes, terabytes. All of those are very, very common in computers. And so the symbol for those values, pretty straightforward. We got a lowercase k for kilo. Let me make that a little bit more lowercase. And we've got capital M for mega, capital G for giga, and finally T for tera. Now let's look at prefixes that are used to make numbers smaller. And so if we had a factor of, let's say, times 10 to the, let's start with, I'll put a times there, that'll make it a little more obvious, 10 to the negative 1. Then we'll go to 2. These are common ones, so I'll put them in. But other than that, we go by 3s again. So 10 to the negative 3, negative 6, negative 9. Should we go to 12? Sure. 10 to the negative 12. That's probably where we would have stopped a little while ago, but technology has been giving us smaller and smaller objects. So we've got to go to 10 to the negative 15 because 10 to the negative 15 meters is a value that is used in science and technology now. So what are the prefixes that correspond to these values? Well, if you think about meters, it should be pretty easy. If I had a meter and I had a tenth of a meter, or 10 to the negative 1, that would be called a decameter. And so we call this a deci or a deci. 10 to the negative 2 is, of course, centi. Again, I learned that from centimeter. And if I get even smaller, I have a milli. And now we go by factors of 6. And so we'll have micro. And eventually technology has gotten to the point where we need to talk about nanos. So you've heard of nanotechnology. That means technology on the scale of 10 to the negative 9 meters. These are very, very small objects. But other technology is going even smaller, specifically ones with related to lasers. So pico gives us 10 to the negative 12. And you may not know 10 to the negative 15 is called a femto. Femto. There we go. And so now we need to represent that by a symbol we can just put in front of our unit. It could be a second, could be a meter, could be a, well, probably not the, anyway, so it could be kilogram too, or a gram in that case. So we've got ourselves D for deci, C is centi, and we very quickly realize we've run out of M's. Big M is mega, little m is milli, meaning micro needs a new letter. And we'll use our first Greek letter of physics, which is a mu. This is the Greek letter mu. You'll see many, many more Greek letters eventually. And that gives us micro. The rest of them are all English. Little n for nano, little p for pico, and little f for femto. And so when you are using prefixes, or even when you're reading prefixes, you should always make sure that the number in front of the prefix, whether it's nanometers or femtoseconds, etc., should be a number between 1 and 1,000. You don't want something larger or smaller than 1 or 1,000. Otherwise, you should be using a different prefix. So let's write it like this. Again, no one's requiring you to use prefixes, but you do need to be able to read them. So try to keep the number in front of the prefix between 1 and 1,000. All right, there we go. Another important piece of physics language that we need to be aware of, especially in laboratories, but also when we're doing problem solving, is the idea of significant figures. Now, I know most of you have heard significant figures before. I want to give you just a quick, easy way to use significant figures so that when you're presenting your answers, they're not overly unnecessarily accurate. They're the right amount of accurate. And that's essentially what significant figures are for. Significant figures tells us with confidence how many digits of accuracy our value is. How much can you trust an answer that you're given? Well, giving the significant figures tells us how many decimal places or how many significant figures we have in a measurement or a calculation or something like that. And that's important when we're trying to understand what we know about a quantity. So basically what I'm saying is anytime you're presenting a final answer, whether it's in a laboratory and especially in a quiz, test, exam, I want you to present your final answer, let's say a final calculated answer. Use as many terms as the value in your calculation with the fewest number of significant figures. That's pretty straightforward. So what does that say? Basically, it's saying, look, if you're doing a bunch of calculations, it's okay to keep a couple of extra digits. Let's say you're doing a calculation between 3 different numbers, and one of them has 3 significant figures. And a significant figure is a non-zero number. It can be 0 in between, but you can't have zeros at the start or the end. Those zeros are insignificant. A 0 in the middle of a bunch of numbers is significant. So out of your significant figures, you can do a calculation, and as you're doing the calculation, keep some extra digits. That makes sense to do. But when you're presenting your final answer at the end, you have to make sure that you have the same number of significant figures as the quantity that first went into the calculation that has the fewest number of significant figures. If they all have 3, your final answer has 3. If they all have a variety, let's say 4, 3, and 2, then your final answer would have 2 as well, the fewest number. And that's as accurate as you can be. You can only be as accurate as your least accurate or significant value that you're using. Let's do a very, very quick example of that just for your notes. If, for example, I have a length of 3.43 meters and a time of 2.40 seconds, and let's say that I'm asked to calculate the speed. And that speed is based on taking the length. I'm not teaching any physics here, just a little bit of sig figs. And I'm dividing it by the time, 240 seconds. Maybe this is the speed of a snail or something like that. We end up with 0.0142916 meters per second. Try that on your calculator. Maybe that's the number that your calculator is telling you. And if this is your final answer, you will probably lose marks because you are saying that your value is this accurate, and it's not. It's not that accurate. It's only as accurate as the least significant value that you have. Oh, sorry, that looks like 2.40 seconds. That should be 240 seconds. There we go. And so when you're presenting your final answer here, you have to do it in the same number of significant figures as the least significant number. And in this case, this one has 2 sig figs, this one has 3. 1, 2, 3. This one just 1, 2. The trailing 0 is insignificant, meaning that the speed we present at the end should be no more than 0.014 seconds. That's it. And that's fine to write like that. That's a small enough number. It's not too small that you need to necessarily use scientific notation, but you absolutely could. And write this as 1.4 times 10 to the negative 2 meters per second. And that is mainly all you need to know about significant figures. So the last little bit of the language of physics that we want to present to you before we get into any real physics is something that is very useful with regard to the conversion of units. This is happening all the time in physics, and so we want to know what is the best way to convert units from one kind to another. And so even though SI units is definitely our preferred unit of presenting your final answer, sometimes you're given questions in other types of units, and so the question is, how do we get them into a form that we're able to use? And so basically, when you're converting from one type of units to another, you need a conversion factor. So to convert units, conversion factor. And basically all a conversion factor is an equivalency saying that one amount in one unit is equal to another amount in another unit. One that is very well known is the idea of a mile. We all hear miles, usually on American TV and media, but how do we go from the standard meter to a mile? Well, instead of looking at a meter, what if we wanted to convert from a mile to a kilometer? Well, to about 3 significant figures, 1 mile is equal to 1.61 kilometers. That's not exact, but it'll do for our purposes. And so that is an equivalency. 1 mile equals 1.61 kilograms, 1.61 kilometers. But to actually use it to convert, what you need is the fraction of one over the other. So 1 mile divided by 1.61 kilometers is equal to what? Or, conversely, if you're not sure, 1.61 kilometers divided by 1.00 miles is equal to what? It's equal to the same thing. If those two things are equal to each other and you're dividing one by the other, regardless of which one is on top, the answer is 1. And as we know, the number 1, we can do anything we want with 1. We can multiply by 1, we can divide by 1, it doesn't change the problem. And so if this value is equal to 1, we can multiply it by some quantity that we have to convert the units. This is our conversion factor. And all conversion factors always equal 1. Always equal 1. So basically you have to know what one quantity is equal to in terms of another. 60 seconds equals 1 minute, for example, or 1 hour equals 3,600 seconds. Well, those things are equal to each other, and so if I put one on top of the other, I'm creating a conversion factor because it is equal to 1, and therefore I can multiply it by what I like. And so we're going to do a little example of this. We'll do an example of my very first car that I had. So my first car had an odometer reading when I got rid of it. Of, prepare to be impressed, 352,178 kilometers. So that sounds like a huge number. A little less huge when it comes to miles. And so the question is, how many miles had it gone? That's it. It's just a conversion question. I've given you a quantity in kilometers, and I want you to calculate it in miles. And so please go ahead and do that. Now, obviously, you're going to multiply by a conversion factor, but which one? Which one will you choose? You can pause the video at this time and try that with one of those values that you think will get you the correct answer. All right, so what we're going to do now is take our distance here, we'll call it L, equals 352,178 kilometers. By the way, approximately the distance from the Earth to the Moon. Not bad. That is a large distance. And I'm going to multiply it by the factor that allows me to get rid of kilometers and convert to miles. And that's going to be 1 mile divided by 1.61 kilometers. Why? Because these will cancel out from one another. The kilometers will convert or will cancel, leaving us a value in miles of 2.19 times 10 to the 5 miles. And why I've only given you the value to 3 decimal places is because that's how accurate my conversion factor was. That was the limiting thing in this value. And so basically it's 219,000 miles I drove in my car. Feel free to guess which car or what type of car I had that was able to drive such a huge amount. All right, one last example and then we'll wrap it up. The last one is one you'll be using many, many times, so I want you to get used to, and that's converting kilometers an hour, a very common unit of measure in everyday life, to its SI units. And so this time we're not using an archaic unit like miles, we're using a version of meters, this time kilometers, a version of seconds, this time hours, but we want to convert them into the SI units, which we know are in meters per second. And so once again, we start with 119 kilometers per hour. This time we have 2 units that need converting, the kilometers and the hours. So we'll need 2 conversion factors. We start by writing our first conversion factor with the kilometers at the bottom because I want to cancel those kilometers out. The second conversion is going to have hours at the top. Then I realized that I want to go from kilometers to the SI unit of meters. I want to go from hours to the SI unit of seconds. Well, the question is, how many kilometers go in a meter, or how many meters go in a kilometer? We know from our prefix that there are 1,000 meters in 1 kilometer, and we know there's 60 seconds in a minute and 60 minutes in an hour. 60 times 60, 36, 3,600. So 3,600 seconds is in 1 hour. Make sure your units are canceling out. The kilometers and the hours canceled out, leaving us only with meters per second. And if you throw that into your calculator to 3 sig figs, you should get 33.1 meters per second.